Okay, probably last video. I don't know, we'll see if we can get through it all, but we're going to talk about work, power, and energy. So, when we talked about energy, we learned that we have conservation of energy. So, our potential plus our kinetic equals the same value all the time. That's our mechanical or our total energy. Potential energy that we talked about is due to gravity, gravitational potential energy. So it's due to your position, like you're at a height above the earth, and it's like a stored energy where you're waiting for gravity basically to act on you and cause you to start moving. We use mass times g times h there. And then kinetic energy is our energy of moving. Okay, you've got to be moving to have kinetic energy, and that's 1/2 times mass times v squared, where v is velocity. We also talked about work and power, and the first few questions are on those, so I'm going to talk about those as we go through. So, the transfer of energy by a force that causes displacement is called work. So, work is our force multiplied by the distance we move something. So, if we apply a force to something and we move it a distance, then we're doing work. Work is only done when the force and the distance are parallel. They got to be in the same direction as each other. Okay. If an object doesn't move, then we're not doing work. Even if we're pushing on it really hard, if it's not moving from a physics definition standpoint, we're not doing work. If we apply a force to an object and it moves perpendicular, so they're at a right angle. So, say we're doing work, but the distance is perpendicular to that, this is force. Then work is not done. Okay, they've got to be in the same direction. So you got to be like pushing something and moving it in the same direction in order for there to be work. And that's why work is not done when we're carrying an item, because when we're carrying, let's say I pick up my calculator, I'm overcoming the force of gravity. So my force is in this direction. But then if I started carrying my calculator across the room, I'm going to be moving in a direction perpendicular to my force. That's not considered work. Okay. It really has to do with angles, which we don't have to get into in this course. Okay. Just really what you need to remember is that work is only done when the force and the distance that it causes you to move are parallel, they're in the same direction. If you and a friend apply the same amount of force to an object, but you move the object a greater distance, you're doing more work, okay, because it's force times distance. So if your D number here is bigger, then you're doing more work. You do 500 joules of work in 10 seconds. Your friend does 500 joules in 5 seconds. Okay, so this talks about power. Power is work divided by time. So if I'm doing 500 joules in 10 seconds, that's going to give me, hang on. Okay, 50. That's going to give me 50 watts of power. If my friend does 500 in less time, 5 seconds, they have 100 watts of power. Okay, so my friend has greater power. And just a refresh on a few things as far as units and stuff go. Energy and work are both in units of joules. Okay, joules or capital J. And then power is in units of watts. Think about light bulbs. You buy light bulbs in units of watts. Okay. So we divide our work by the amount of time over which we do it, and that gives us power. So in the case of this example, me and my friend both did the same value of work, the 500 joules of work, but my friend did it in less time than I did. So that means my friend has greater power. Okay. Okay. few other things here on work. A box is pushed across the table, overcoming friction. Forces at work on the box are it's really, if you're pushing something across the table, you're always going to have weight. You're going to have normal force, and if we're on a table, those two are going to be balanced. Then we're also going to have an applied force because we're pushing it. And we're going to have friction. We said overcoming friction. That means we do have some friction. We're just pushing it enough to overcome that. Another example, a pulley rope raises a box and there is air resistance. So forces here are going to be the weight of the box. Okay, so we're overcoming that weight in order to pull it up. But then we're going to have an air resistance that's offsetting that. Okay. In the case of this scenario, we're not on a surface, so we don't have normal force. We don't have surface friction. We're raising the box, so we are making a force to raise it, but that force is equal to the weight of the box. Okay, and then it's going to be offset by an air resistance. How much work is done when a 50 Newton force moves an object 3.8 meters? So we're going to do work force times distance. We're going to have 50 times 3.8. Okay, so there's my force, there's my distance, and I'm just going to multiply those. 50 times 3.8 is 190, and again, that's in joules. Okay. Okay, I think the rest of this is energy. I think we can get through it. Let's keep going. All right. Stored energy that depends on an object's location is called potential energy. We talked about that a few minutes ago. And then energy of motion is kinetic. So potential, m times g times h. Kinetic, 1/2 times m times velocity squared. Raising a box off the ground is going to increase its potential energy because it's going to increase this h. You raise an object to twice the height it was before, that means its potential energy will double. Okay, if this number is twice as much as it was, then this number is going to be twice as much. An object's speed doubles. Its kinetic energy, okay, now here we got to remember the square, right? If this number doubles, it's actually doubled squared. So it's going to quadruple our kinetic energy. Okay, whenever you got a square in an equation, you got to keep that in mind when you're thinking about relationships. Okay, conservation of energy. Energy cannot be created or destroyed, only converted or transformed. That's the law of conservation of energy. So that means our total initial energy has to be equal to our total final energy. And we looked at that a lot when we did things like the roller coasters. You know, we use that total energy going along to help us figure out the kinetic and the potential. Objects have no kinetic energy when they're at rest. Okay, if you're not moving, then if this is 0, then your kinetic energy is going to be 0. And they have no potential energy when they're on the ground. Again, if your height is 0, your potential energy is going to be 0. You raise a box to a height of 8 meters. When at this height, okay, it's going to have potential energy only. Okay, so say we raise the box and we're just holding it at rest. That means it's going to have potential energy there. Then we drop it. Halfway down, it's going to have both kinetic and potential. Remember, so let's say we've raised a box. Okay, so this is our first point. We've got potential energy. Then we let it go. It's falling. We're going to have potential and kinetic here because it's moving, but it's also got height. Okay, and then just before it hits the ground, it's going to have kinetic energy. Really, this says after it hits the ground. It should really say like just before, because that's when it's going to be moving the fastest, right before it hits the ground. So we go from all potential to some of each to all kinetic. So here we've got all height. Here we've got some height and some moving. And then here we've got all moving. And that's what we looked at with the roller coasters, like a bunch of different times. Okay. You raise a 3-kilogram book to a height of 6 meters. How much potential energy does the book have? So we're going to do mass times g times h here. So we've got a mass of 3 kilograms. G is still our 9.8. Our height is 6. We're just going to multiply all those guys together. That gives me 176.4, and that's in joules. And then if the final velocity of this 3-kilogram book dropped from 6 meters is minus 10.44 meters per second, what is its kinetic energy just before it hits the ground? So we could calculate all that out. That would be kind of a pain. We could also say that we know our total energy is conserved. We know at our initial point where we're holding the book at this height, this is our potential energy. And then just before it hits the ground, all of its energy has been converted to kinetic. So our kinetic's actually going to equal the same value as our potential was. So we could also multiply all that out. We would have 0.5 times 3 times 10.44 squared. Let's see if we get the same number. It's not quite the same number. But if we're going off of conservation of energy, which is really what we want to look at, then this is all potential at this point, and then it's converted to all kinetic just before it hits the ground. Okay. All right. So that is all of our study guide. Good luck reviewing.